what we're calling ourselves is a think and do tank here at the 2035 initiative. And I'm going to briefly talk about how this unique blend of rigorous engineering analysis and rigorous policy analysis is we think going to help accelerate industrial decarbonization. The types of decarbonization opportunities we're talking about today relate to low and medium temperature process heat. So on this slide, you can see different temperature ranges for different major US industrial sectors. Around half of all the process heat used in US industry goes into what we would call low and medium temperature process heat. This is heat that is less than 300 degrees C. Now that's hot by human standards, but low by industrial standards when we're talking about heats of greater than 1000 C for heavy industries like iron and steel and cement. And the findings that I'm going to discuss today, we were very excited about. So what we found was that there is a real opportunity in the US to start decarbonizing industry today by focusing on low and medium temperature process heat, primarily in the three major sectors that account for the majority of low and medium temperature process heat. That's food and beverage, pulp and paper, and chemicals. We think that we can reduce up to a quarter of their climate emissions by focusing on low and medium temperature process heat and deliver a lot of health benefits to U.S. communities, which I'll talk about. We also consider energy efficiency. That's the first fuel in any plant upgrade. We find that, again, it's a win-win, and that a lot of these opportunities are cost-effective today, but we certainly need policy support to seize the full opportunity space. So there are many technologies that we have already in hand off the shelf or which are being piloted, which are electrified technologies for replacing combustion in low and medium temperature heating applications. These are some of the technologies you see in the today column. There are also technologies coming down the pike, which will even open up more opportunities moving forward. Our research question in this project that I'm going to talk about today is, where is the most technologically and economically feasible opportunities to electrify industrial process heat? And we're talking about in the near term. Where are there opportunities now? We focus this analysis on four main technologies. As you saw 2 slides ago, there are a lot of different technologies that are electrified that can be used to replace low and medium temperature process heat. But these 4 technologies are ones that we found have a really large potential today. And I should mention also that low and medium temperature process heat, a lot of it relates to steam generation and processes that are running at temperatures achievable by steam. So we looked at 2 technologies in the top row for replacing the primary generation for steam. These would be industrial electrode boilers. You see a picture of that here. These are mostly drop-in solutions because a lot of the infrastructure stays the same. You just need to upgrade your boiler to an electrode version and have sufficient interconnect. And then there's more of an advanced solution here on the right, which is an air source high temperature heat pump. This is an emerging class of heat pumps that can be used in industrial facilities that can reach higher temperatures than traditional heat pumps. We also looked at electrified ovens and electrified dryers because these 2 technologies have a lot of applications in the food and beverage, pulp and paper, and chemicals industries. And of course, there's no one size fits all for any industrial plant. So we looked at 4 different scenarios and we compared those scenarios to the baseline. We're calling our scenarios drop-in electrification. This would be an electrode boiler and replacing dryers or dehydrators or ovens wherever they exist. And we also have a variant on this scenario where we looked at maximizing energy efficiency. In the advanced electrification scenario, instead of using an electrode boiler, we're using a high temperature heat pump because that takes a bit more engineering at the plant level. We also looked at a variant where we're optimizing the efficiency of the plant while we do the upgrade. And the way we approach this as engineers is we use detailed process archetypes. So these are engineering mass and energy balance models of typical plant configurations. We looked at 33 different types of plant configurations across our sectors of interest. And, if you're engineers and you probably did this in some of your training, having a digital twin, a simple digital twin of a plant gives us the opportunity to explore what if scenarios. So if we capture all of the mass flows, all of the heat flows, we consider heat integration, we consider real world complexities, we can use these models to, for example, drop in an electric boiler and simulate how much fuel is reduced and how the emissions change. We can look at it replacing the dryer and meeting the amount of heat and throughput required there. In our advanced scenario, we did that by looking at air source high temperature heat pumps, as you see here. And the other thing I want to stress is because we've modeled these operations from the bottom up based on real world technology parameters and plant characteristics, we can also look at a wide range of efficiency opportunities when we simulate our scenarios, including things like upgrading process controls and insulation and recovering waste heat. So these were very rigorous models that we used, and here are some of the results. For our four industries, what we're seeing here is that alongside a clean grid, electrification can certainly reduce industrial pollution, but it also is going to take some time. So in this graph, we're seeing the baseline emissions from our scenarios in focus, and we're seeing our four different scenarios colored in shades of orange here, I guess, or yellow, from left to right. And what we can see is under traditional sort of drop-in solutions, an electrode boiler, there are many places in the country where it actually will increase emissions today because the grids are still dirty. But over time, as the grids become more reliant on renewables and the carbon intensity drops, all types of solutions work. Where advanced electricity, meaning the high temperature heat pump, has an advantage is that it's much more efficient. We're not creating heat through combustion. We're moving heat into the system by moving it from the outside, essentially, and valorizing it. So in some instances, in many parts of the country, advanced electrification can reduce emissions compared to combustion today, even with less than optimal grids. We also want to consider the grid loads. So what you're seeing here is a map of the additional grid loads that we would see if we tapped only the first 25% of the opportunity space. And here in the US, you may have heard we're dealing with a lot of grid stress due to new grid loads, due to data centers and so forth. So we also wanted to explore, would industrial electrification pose undue grid stress? And what we're finding is that in most parts of the country, at least in the near term, the additional loads are pretty minor compared to some of the other loads we may be adding. The economics, of course, are really important. So in the technical analysis, as engineers, we can always say, yes, this technology, if you install it, will save energy, it will reduce emissions, and it could be cost, but we don't know how cost effective it is. This is critical for crafting policy because what we found is that electrification has two major challenges. The first is that upfront costs can be steep. So what are we seeing here? We've got our four scenarios: drop-in electrification, drop-in with efficiency, advance, and advance with efficiency. There are some scenarios where drop-in electrification under optimistic cost conditions, meaning lower capital costs, lower installation costs, could be cheaper actually than the baseline of replacing your systems with natural gas boilers. But for most of the variants we analyzed, costs did go up on an upfront cost basis. And that means really we have to rely on the OpEx, the change in energy costs, for making the investments attractive. It's a challenge in the US. So what you're seeing here is a map of what we call the so-called spark gap. This is the ratio of the electricity price to the natural gas price. And what you can see here is in most parts of our country, electricity is more expensive than natural gas, meaning even though we might save on the amounts of energy needed to provide low temperature process heat, because electricity is much more expensive, sometimes by a factor of 8 to 1 in the eastern parts of the country, suddenly now the energy bills go up. And what that means is there are some plants in the US today under favorable price conditions, low spark gaps and low temperatures, where installing these technologies can achieve positive, attractive payback periods today. But if you look at the y-axis here, we're talking about only 5 to maybe up to 10, close to 15% of plants where it's cost effective today. And what that means is we need policy support. So our policy analysts did a lot of wonderful analysis and looked at a wide range of policies that could be deployed in the US for making these investments more cost effective. So, subsidizing electricity rates, subsidizing CapEx, really subsidizing electricity rates as we move from left to right here. And then finally offering a tax credit or a clean heat credit. So to plants who install clean heat technologies, based on the amount of heat, they get a credit. We saw that with the more aggressive policies, these payback periods become within reach for nearly all US plants. And so our policy recommendations were we need to reduce risk and capital expenses for these investments. We clearly need to reduce OPEX, especially in places where we have high spark gaps. We need to leverage efficiency in these projects to make everything more cost effective. The beauty of efficiency is if you upgrade the efficiency of your plant before you install your electric boiler or heat pump, you can sometimes reduce the needed capacity for that replacement. We need to raise demand for clean products, eliminate fossil fuel subsidies, and create lots of technical assistance, especially when it comes to high temperature heat pumps, which are a fairly new technology. I'm going to close with just summarizing that we also considered co-benefits. So climate change is certainly an important problem that we want to address. We need to begin decarbonizing industry today. But if we do so, it implies replacing combustion technologies with clean electric technologies. We can also see many large co-benefits for communities who are living around those industrial plants. So we estimated that hundreds of billions of dollars in cumulative health benefits would accrue if we were to electrify low and medium temperature process heat. This would translate into more than 1 million lost workdays avoided, millions of asthma attacks avoided, and millions of lost school days avoided. So there are serious human health benefits that would come along with these investments that policymakers need to be aware of because they also have goals for protecting public health.